All right, thanks, Kendrick, for that intro. Yeah, I'm happy to present to you guys. So, first off, what is network assurance? I'm going to talk a little bit about our story of how we use MongoDB and some of the problems we ran into, some of the limitations and the constraints we had, and how we solved them. And we'll go over some optimizations, and possibly maybe you could use them for your products. So, network assurance is the guarantee that the network is doing what the operator intended it to do. So in this talk, I'm going to mention intention and intended and operator and engineer and kind of policy of what the engineers want the network to operate like. And ultimately, our product kind of assures that this is happening in the network. In the modern data center, a lot has changed in the last decade. First off, we used to deploy on a matter of months, but now the expectation is you're deploying in a matter of hours. You have servers that used to be maybe 10K data centers, but now there's easily 100K servers, and then going close to billions of servers and devices all connected to the network. So you can see it's getting more and more complex. And then also the expectation is that you're able to deploy an app, let's say on the US East, and be able to migrate it very easily over to the US West in a matter of hours. And then all at the same time, security, we always want to maintain security and at very high level. Even though our applications are getting more and more complex, they have services everywhere and they're all talking to each other. But security is, a paramount concern. So on the right, you can see so many stakeholders that are pushing their changes, making sure that their changes get automated and pushed into the network. So a lot of things there's a lot of moving parts, and our product makes sure that all these moving parts, we're not making mistakes during that time. So I want to introduce more of a policy-based data center. Prior to like a policy-based data center, you'd have all these groups just manually configuring their scripts and pushing out their changes. And you could see this could be quite error-prone. But instead, a policy-based data center, all these groups are actually interfacing with a controller. And it's like a well-defined API and interface where this controller actually pushes out these changes and automates the process a lot more. It does translate this like high-level intention and policy of the engineers and the operators, and then kind of translates it through the network layer. And things can go wrong along the way. There could be bugs, and that's where our product actually fits in, to make sure that things are not broken. In this simple example, you can see a typical web tier, an application tier, and a database tier, some firewall rules between them, and some, just like, for example, the web tier can only talk to the application tier. The application tier can only talk to the database tier. You want to make that secure, and those policies, that make sense. So our product actually had quite a few constraints. We did want to support the smallest customers and also the largest customers. And so we did need to work on multiple form factors, down from, at the lowest level, a personal laptop, which has limited memory, solid-state drive, to the next level of a lab environment where we're spread across multiple VMs and hard disk drives with limited storage, and then ultimately to production, where you have a mix of hard disk drives and solid-state disks. But one of the main constraints that we dealt with Mongo specifically was that we had to constrain our wire tiger cache. And your wire tiger cache is so important because if you have large amounts of data, these indexes need to fit in the cache for your performance for you to have good performance. That's like a basic database principle. So we're kind of pushing the limits there. We weren't able to just tell our customers, hey, just give us hundreds of gigabytes of wire tiger cache and we'll perform well. But so we had to limit that based on the customer requirements and the needs. So we had a lot of different kind of flavors to deploy. Another thing that we needed to maximize was the write throughput, because we are kind of pulling the data from the network every timestamp, and we're ingesting a large amount of data into Mongo. So we needed to think about our write throughput and make sure we didn't compromise on our reads either. And in terms of reading, query flexibility was very important to us, and a flexible document store was important, and Mongo fit in well. We actually started on Postgres, and we found that it was a little too rigid, and we actually migrated to Mongo, and it proved to be a very good decision. We use the aggregation pipeline of Mongo pretty heavily, and that's worked out pretty well for us. So this is how our application sits in the network. It sits on VMs outside or inside the network and across multiple VMs, and we just continually pull data from the network. All the routers and switches have a lot of information that we gather. This controller that sits on the side is what I was telling you about for the policy-based data center, where it's actually automatically pushing and translating the intent that the operators want to the network. And here's a little bit about how our streaming pipeline works. We gather information about the policy, which is, let's say, the database tier can only talk to the application tier. And then also about the infrastate, which is actually how the packets route through the network. We do crunch all this data, and we analyze it with formal methods, which is an area of computer science. And then we store all this information in Mongo and then present it to the user. And here's a little, just a little bit on a UI. So this is our search and visualization page. As you can see, there's like an orange arc, which highlights that there's a problem between the app and the DB layer. So the user is able to easily just drill down when they click on it to kind of figure out what's going on. We do capture all the problems or info or whatever that we want in events, which are, we're trying to capture what, where, why, and how problems occur. And this is our bread and butter collection. This is the collection where we have hundreds of millions of documents, and this is the collection where it's the hardest to manage. And we're going to tell you a little bit about how we managed it. And then obviously once we have a problem, we do suggest next steps for the user to alleviate the problem. All right, so enough talk about the network assurance engine. I want to focus more on Mongo now, and about what our product, how Mongo is used. So when I'm talking about high volume time series data, I'm referring to about 12 million time series data points. So that's the number of documents that we ingest per hour in our largest fabrics. And for our UI, we want to show a look back of probably a couple hours so that we show the trends in the network of what's happening. Also, we want to allow the user to scroll back many months so that they can see the change in their network too. So you can see that we're kind of traversing a large amount of data during that time in the UI. So it's very tricky to figure out how to do that well. We do use a streaming data platform with a 3-tier typical web stack that's backed by Mongo database. And on this diagram on the right kind of describes our main challenge. So the event collection, which is the one that's hundreds of millions of documents, and it just keeps growing. And the triangle above it, we call it the random access index, which is the default index in Mongo, is this large triangle above it. And it's shaded because the most recent documents that we're interested in is kind of spread out through this index, this triangle. And then the square on the right is our actual WireTiger cache. You can see that the triangle is larger than the square. So we are breaking the rule of database design where the index is larger than the WireTiger cache. And that's where we hit a lot of problems once we started deploying on large fabrics. So the agenda for this talk, we're going to talk about optimizations we made in B-tree indexes. We're going to talk about date interval partitioning. And then we're going to talk about some system configs that helped our write throughput. We're also going to talk about some tricks, such as pre-aggregation, that helped us query our data in a very efficient manner. And then we'll talk about a replication factor, which we tweaked to increase our write throughput. And here's Tom Monk to start it off.
Thanks, Gabe. So yeah, when we first we were given this problem, and we felt like we were kind of given an impossible task. There's a little bit of resistance at first, We were maybe a little bit angry that we were not given the number of resources that we would really need to actually solve this problem. But then we started really thinking more about the problem that we were given. So we have terabytes of data, we have gigabytes of index, and our WiredTiger cache is not even big enough to fit most of our indexes in memory. And so this caused a lot of concern for us, and sure enough, when we first started testing with large fabrics, the first problem we ran into is that after some time, after we had been running for a few days on a large fabric, suddenly the Mongo writes would just kind of slow to a crawl. And this kind of confirmed for us that we were not being given enough resources, so we went to management and said, hey, we need more resources. They said, no, we need to we need to keep the form factors small to meet the constraints for our customers. So that forced us to kind of think hard about the kind of data that we were storing in MongoDB. And we realized that the kind of data that we're storing in MongoDB is a very special kind of data called time series data. And time series data has very special properties. So typically in time series data, you're always writing the most recent data. So whenever you're doing an insert, that insert is going to be the most recent piece of data that you have for that time series. And also with time series data, very frequently the customer is the most interested in the most recent data, so maybe the past 24 or 48 hours of data. And it's these properties that allowed us to solve this problem. So I keep using the word time series data, and I wanted to give a concrete example of exactly the kind of data that we're talking about. So this is just one of the data points that we collect from the fabric. This happens to be the hit count for a particular security rule on a particular leaf switch, and we collected this at exactly 8:20 on May 14th. And we can see that this security rule has been hit by about 934 billion packets. So we just have a very large number of these data points coming in. We need to store them. And of course, we're a data center application, but there are a lot of examples of time series data. Stock ticker data is maybe one of the very first versions of a time series data stream. HTTP logs would also be considered time series data. And even the Twitter fire hose, you could think of that as time series data also. So also when I get into talking about exactly how we optimized our B-tree indexes, it helps to just kind of refresh our memory about exactly how B-tree indexes work. So MongoDB indexes are stored using a B-tree data structure, and all of the keys in the B-tree data structure are kept in sorted order. A B-tree is a kind of binary search tree, except instead of having 2 children per node, you can have many, many children per node. And so here's a sample B-tree index. You could think of this as an index on the _ID field in a Mongo document. And it's just a bunch of numbers. So every time you insert into a collection, every time you delete from a collection, or every time you read from a collection, MongoDB is going to be using this index to make those operations efficient. And so it's also important to note that every time you insert, MongoDB also has to update this index. Every time you delete, MongoDB has to update the index. So there's a lot of, when you have a heavy write volume, there is a lot of update activity happening on your index. And so typically for non-time series data, the access pattern for an index is kind of random. So for example, in an e-commerce use case, maybe you have an index on your user collection for the user ID. It's impossible for you to predict the order in which the users are going to log into your application. When the user accesses your application, you need to have all of the entries, all the keys for that user in memory already. You can't switch back and forth, paging in and out of disk into memory, all the different index keys for the users. You pretty much have to have the entire thing in memory in order to have efficient lookups. And this is why it's a law in database design to make sure that your indexes fit in memory. And this is where the time series data comes in. So there's these very special properties of time series data allowed us to optimize our indexes by creating a compound index with timestamp as the first field. And what we noticed then was that whenever we were doing inserts, MongoDB just had to traverse the right-hand edge of the index to insert the key. And even when we were doing reads, because our customers were accessing the most recent data, let's say the last 24, 48 hours most frequently, that was the data that was most interesting to them, then MongoDB only had to keep kind of the right-hand segment of the index in memory. So this allowed us to drastically reduce the amount of memory that was consumed by our indexes, and really was a key to solving this problem that we had. And so this just illustrates that. So we're breaking the law. You might say, hey Tom, you're crazy. You can't even fit your indexes in RAM. But we did it on purpose. This special property of time series data allowed us to page out a huge chunk of the index and keep only the most recent edge or most recent documents in memory. And if you read the MongoDB manual, there are some hints that this is possible with MongoDB. So there's a whole section in the manual about how you need to make sure that your indexes fit in RAM. And we were reading through this section when we started facing the performance problems that we faced. And it made us kind of nervous because it goes into great detail about how it's very important to make sure your indexes fit in RAM. But at the very end of that section is a little blurb that says, oh, by the way, if you have a field that increases monotonically over time and your use cases cause you to access pretty much only the most recent values of that field, then you might be able to get away without storing the entire index in memory. And we kind of seized on that, and that was the hint or the clue that allowed us to kind of solve this problem. And there's another beautiful property that comes from putting the timestamp first in a compound index for Mongo, and that is that WiredTiger does prefix compression on index key values. If you think of what timestamps look like in memory, the first couple of bytes don't really change much over time. It's a monotonically increasing value, and so the first few bytes stay the same. So WiredTiger will store just one copy of that prefix, the 5AB9, per page per node in the B tree index. And it effectively cuts in half the key size that you have to store. Instead of having 4 bytes per key, now we really only have to store 2 bytes per key. And this might look familiar if you look at object IDs, the default object ID values in Mongo, because those default values also have a timestamp as the first 4 bytes in them, and you get the same kind of common prefix among those object IDs. And this kind of was confirmation to us that we were on the right track on how to organize our indexes for MongoDB for these time series use cases. And now I'll hand back to Gabe. He's going to talk about a further refinement that we did on top of this called date interval partitioning.
All right, so we're humming along using our B-tree index optimizations. Actually, in our team, we called it the right-sized index. And you can see in the triangle again, this evolving triangle through the talk, that it's no longer shaded across, but instead, we only focus on the right-hand side of the index. And you can see that shaded portion can actually fit in the square. So performance is good. We're able to serve the UI. We're able to ingest data at a high rate on large fabrics. And then, of course, a feature requirement comes in. And that feature requirement is, hey, I'm a customer and I want to purge my data that's older than, let's say, 6 months, or I want to archive it off. And so we started building out this feature, and we were like, okay, well, we'll just simply, delete the data from the event collection on this index field. So we're just deleting millions of documents, and we have this asynchronous batch job that does it in our appliance. And then we deploy, and we're running, And then we just see our disk utilization just spike to 100%, and it's just pegged there. And our write throughput is just crawling. Our read on the UI is barely loading. And then we could see that actually these deletes of the millions of documents, they're taking like tens of minutes. And we said, obviously, this is not going to work. So we talked to our MongoDB consultant, Mike Laspina, he's in the back, and he said that, hey, you know what? MongoDB Cloud Manager, they use date partitioning. We might want to think about that. So we investigated it, and it actually worked out pretty well for us. So here's how it looks. So data interval partitioning is basically splitting up your huge collection into multiple small collections. And in this example, we're going to split it into days. And so we have some days in May and June shown here. But essentially, all these collections are your one logical event collection. And then, as you can see, these collections will easily fit in the WireTiger cache, so you have that performance. And then one added benefit, actually, so this addressed the main concern, because dropping a collection doesn't take tens of minutes. It's actually instantaneous, on the order of less than a second. And then an additional benefit is that when you drop a collection, you actually give the disk usage back to the operating system. So if you do a df-k, you'll see your disk usage actually lower. But if you actually ran a Mongo delete, maybe some of you know this, Mongo actually doesn't give you the disk usage back. So if you do a df-k, it will be exactly the same, because Mongo likes to hold on to that disk usage, hopefully using new documents to insert in those positions. So it kind of simplified our disk usage calculation. That helped us out a little bit. But the main concern was achieved, because now we're able to drop data very quickly. So that worked out pretty well for us. Yeah, so the feature was pretty good after that. And we were able to deliver that feature. So now I'm going to move on to a little bit more about system configurations. And we started deploying, and the question we had here was, how come we're not getting the write throughput that, let's say, a hard disk drive or a solid state drive advertises? I want to get as much write throughput as I can. So we tried to look for every single detail, and as much as we could. We did engage with MongoDB support, and they were pretty helpful. They told us to point us to production notes, and we read them all, very, very well written and easy to understand. But more importantly, they pointed us to a script that's available publicly. It's called mdiag.sh, and it's very simple. You just run this script on your server, and then it spits out all the configs that your system is not adhering to for the recommendations. So some of them were things like XFS is better performance than ext4, or your TCP keep alive settings are not according to recommendation, or enable the swap so that if you have like a huge read, that the operating system doesn't kill your Mongo process. And one of the configs that was specific to our product was the WireTiger cache, and we kind of tweaked that to figure out what was optimal for our system. And then, so another kind of benchmark that was useful for us is there's a Mongo import and export. That it's a tool that's available in the Mongo distribution, and that's made for, I believe, just taking out all the data in your database and importing it somewhere else. So it's written by Mongo developers. So we kind of use that as a benchmark to show that, hey, this is probably the maximum write throughput that we can achieve on our system, given our application and how we use, it's running through our code. So we try to get as close to that as possible. And that was a good benchmark for us. And then here's Tom to talk about pre-aggregation.
So the data interval partitioning was a great enhancement for us and allowed us to deliver a lot of features that we wouldn't have been able to otherwise. But we also had some use cases in our GUI where we wanted to be able to give users a trend, a view of a trend over multiple days. And this became kind of challenging for us after we did data interval partitioning. But the way we solved that problem was not by trying to stitch together the collections and form the query results from multiple queries. Instead, we did aggregations over those multiple days as the data was being created. So pre-aggregation is just a technique to take what might be a very large data and summarize it in an aggregated view. So here's just one concrete example, and this example actually comes from a paper that was written by Sandeep Parikh and Kelly Sturman. It's a really great post. The URL is there. I encourage you to read that to see more examples of these really great schema designs for time series data. So in this particular case, we have the same data point that we saw earlier, and we have millions of these coming in. One way to aggregate them is to have a summary per rule and per leaf that is over a large range of time. So here we have, like, for the entire day, May 14th. Here are all the hit counts that we observed. These numbers here would be the number of seconds offset into the day at which that hit count was observed. And you can imagine this could be done not just for one particular day, but you could even summarize the data per month, and maybe discard some data points for the monthly aggregation, so that you can show the user in a very efficient way time series charts. And I want to talk about one last optimization that actually massively increased our write throughput. And I think it's probably something that may not occur automatically to some people. It actually didn't occur to us either, but Mike Laspina suggested it to us. So there's actually two different ways to run a 3-node replica set in MongoDB. There's kind of the standard one, which is a primary, secondary configuration, where you have one primary replicating data out to 2 secondaries. And this would basically give you a replication factor of 3. You have three solid copies of your data sitting in your data center, and you can ensure high availability with those 3 copies. You can do W2 writes, making sure that writes are 100% durable. It's impossible to lose a write. Even if you lose a node, you'll always have that write because it was acknowledged by the primary and at least one secondary. And that's how most people run their Mongo. But for applications that have a very heavy write load, sometimes you'll start to run into problems there. So the problem that we saw is that the primary was having a very hard time keeping both secondaries up to date. So in MongoDB, the replication model is that the secondaries pull the oplog from the primary. And when you have 2 secondaries, they're both sending oplog requests to the primary. And if the primary is already under stress because of that heavy write load, it also has trouble keeping up with those oplog queries. So the solution is just to replace one of the secondaries with an arbiter. And the arbiter doesn't actually store a copy of the data. It's just a voting member of the replica set. It kind of breaks ties to select primary when one of the nodes goes down. And so you only have to keep the actual full data on the primary and one secondary. And then there's only one secondary requesting oplog from the primary, and the primary is able to service those more easily, more efficiently. And so one key thing to note is that with a PSA or primary secondary arbiter configuration, you can't do W2 writes anymore. If you try to do W2 writes and you lose one of your data-bearing nodes, you'll no longer be able to write to your database. So the availability would be very poor. If you lose either or, you won't be able to do writes anymore. So you have to use a W1 write concern with PSA. So that comes at a cost of data durability. It is possible for a write to be sitting on the primary and it hasn't yet been replicated to the secondary. You then lose the primary because of an outage. You might lose that write that occurred on the primary because it won't be there on the newly elected primary. But it comes at that availability cost, but the impact on write performance is massive. So we were seeing with a primary secondary configuration with W2 writes, we were seeing around 2,000 docs per second on a single shard. When we switched to PSA with W1 writes, we were seeing around 14,000, so it's a 7x increase in our write throughput. And this was big enough where we had to very seriously consider this configuration change in our network. And it turns out for our use case, because we are collecting data from the network, it's actually okay if we lose some writes in the rare case that we lose a primary. Because in the worst case scenario, we can always just go and recollect the data from the data center. It's not like we had a one-time piece of data from a customer, like a password change, and if we lose that write, that change is lost forever. If we lose some writes, we can just go out and recollect from the network. Everything's okay. So this PSA, it helps you increase your write throughput. It comes at a cost. You just have to consider, make those judgment calls for your use case. Like, is my use case something that can withstand losing some data? If it is, then this might be a really good optimization for you. And yeah, I just want to point out that Mike is the one that helped us with this really great optimization. And this slide just summarizes the things that I just said. There's a judgment call here. You have to make sure that you don't do this optimization without thinking through the consequences. And so now I'll hand back to Gabe. He's going to wrap things up.
All right, to summarize, we made a few optimizations, and the right-size B-tree indexes that Tom talked about earlier, it worked out well for us, but we did choose date partitioning as the final design. And then pre-aggregation was useful for us to persist those intermediate results for expensive queries so that the read throughput would be very high. And then replication factor of 2 and write concern of 1 maximized our write throughput, and it worked out well for our system. And so thanks for listening to our talk. I do want to acknowledge Raghavan Kalivakam as our team lead. He was very instrumental in leading us in this effort. So if you guys have any questions, feel free to ask him. We'll be happy to answer them.
All right, we have time for one quick question. I think I saw a hand here.
Yeah, I was wondering about the B-tree rebalancing, and is there a process that has to happen every night where you swap some of it out, or does Mongo do that automatically as new records get added to the collection?
Yeah, that's a very good question. Mongo actually does that automatically, and it does, yeah. So
the B-tree rebalancing is kind of a recursive thing that goes up the chain. And it's not like you need to have the whole index in memory in order to rebalance. You still only need to have some small section of the index in order to rebalance. And the fact that some of the indexes on disk does kind of slow down the rebalancing, but it hasn't been a performance barrier for us at all. Yeah.
All right, we'd like to thank Gabriel and Tom for the awesome content. Thanks a lot, guys.
Thank you.
Everyone have a great MongoDB World.